right. So I calculate this guy by taking that product. I have negative e to the negative 8t minus this product. I have e to the negative 8t. Looks like I have negative 2e to the negative 8t. Is that identically equal to 0? It is not. What does that tell me? Independent or dependent? Independent. Not equal to 0 means independent, which means in this case I can now form my general solution. It's some constant times the first solution plus some constant times the second solution. That is a perfectly good solution form. Any questions there? All right, wonderful. I have a family of solutions, the general solution. Hopefully in real life this is modeling something, right? This is modeling my population is changing, or the position of a spring, or some sort of dynamic system. And if that's the case, I don't really like those constants, right? I want to have specific values to model my specific system. I'm modeling population. I don't want to have a general solution. I want to know what is the population going to be in 20 years, right? So to do that, I need some initial condition. All right, so over here, for higher order, we get some conditions that might look like this. And we would plug in our conditions, apply our conditions to solve for the constants. Same thing with systems. Over here in systems, though, we might have a condition that looks like this. U of 0. So what is my state of my system at time equals 0? At time equals 0, my solution looks like this. How about 1? That would be an initial condition for my system, giving me the value of u1 at 0 and u2 of 0. I'm just writing it in vector form. Now, how do we use this to find the constants? Well, we just plug it in. It says u is 1, 2 when t is 0. E to the 0, which is 1. Over here, I have this guy times e to the 0, which is 1. And so I get that. How do I solve that thing for C1 and C2 now? What could I do here to solve for C1 and C2? I could do row reduction. Absolutely. I could write this over here. Basically, I have the linear system that looks like this. And in this case, I could then row reduce this augmented matrix, and I could find my values for C1 and C2. Absolutely. And the nice thing about that process is that it's systematic. I can do that if this is a 10 by 10 system, or a 100 by 100, or a 1,000 by 1,000 system. I have a process for that. Okay. Now, for a small system, I could also do this. I could also rewrite that system as a system of equations. This would be a 1 equals C1 plus C2, 2 equals C1 minus C2. I can go back to the equations as well for small systems usually, not for big systems. You don't want to do this. But in this case, I can see I would just add the two equations together. I would get 3 is equal to 2C1. C1 is equal to 3 halves. We have C1 is equal to 3 halves. Looks like C2 would have to be equal to probably a negative 1/2. Kind of plug them in that first equation. And now I have my values. And I could say my specific solution is going to be 3 halves times 1, 1 e to the negative 2t minus 1/2 1 negative 1 e to the negative 6t. Questions there? Yep.
So when we if we do this for test, you want us to multiply it after multiply by the 3 halves and the e to the negative 2t. You want to combine that into 1.
Doesn't matter to me, right? You can if you want. This is a perfectly good solution form. I actually like this form quite a bit because when I see this form, I can see what's happening with those exponentials, right? Both of those exponentials are going to go to 0 as time gets big. So I can kind of see what's happening with the broader system. And we'll kind of talk about a graphical representation of what this means when you look into solutions. You know, you could combine it though. I mean, our solution is going to be a vector. It's going to be a value for u1 and u2. So I could combine this into one giant vector by multiplying the two vectors and then actually adding them together. I could get 3/2 e to the negative 2t minus 1/2 e to the negative 6t, and then 3/2 e to the negative 2t plus 1/2 e to the negative 6t. Like that is also another perfectly valid solution form. I mean, we have a vector u over here, but really that's a u1 and a u2. So that kind of helps you see the individual pieces better. I really don't care which way you write it the form in. You probably work them to get to this point, so you're welcome to leave them like that if you want. Okay. Any questions there about the manipulations? All right. Here you go. Practice for you. Once again, this is stuff that could certainly be on that quiz on Tuesday. Go ahead and work through the 3 problems, and then I have specific questions about pieces of the work that I'll ask for the clickers. See if we're tracking and getting them right here. Show that these two are bases for the solution space. That's the language we're using as opposed to fundamental stats. Same idea. The first question I'm going to ask is, to show they're linearly independent, you got to calculate the Wronskian. What is the value of the Wronskian? 1, 2, 3, 4, none of the above. A little bit mixed, mostly 1. 1 is correct. Let's go through the calculations though, since we're only about 50% there. The idea is I have a Wronskian that has, this is my first column, so that's e to the 1/2 t and e to the 1/2 t. Remember, no derivatives needed here. I'm forming that full column just from that one solution. Over here I have 0 and I have e to the negative 1/2 t. And so when I calculate that term, I take this product, which is e to the 1/2 t times e to the negative 1/2 t, e to the 1/2 t, e to the negative 1/2 t, minus 0, but that's just e to the 0, that's just 1. Then 1 is clearly not identical to 0, right? So this non-zero value tells me they are linearly independent. So they do form a basis for the solution space. It means I can form my general solution as some constant times the first solution plus some constant times the second solution, like that. And then lastly, I got to use my initial condition. When you do that, you have to find C1 and C2. C1 is equal to what? This is the second bigger question. See how we're tracking on conditions. All right, everybody looks like they're pretty happy with C. All right, any questions? So I got over here just to show that I wrote my system out, I wrote the augmented matrix, and now I'm doing the row reduction. When I get to this last piece, I'm basically generating equations that say C1 is equal to 3 and C2 is equal to 1 from that final reduced state there. What? Right here? Right there. That should be a 1. Yes, thank you. Right. So then that should be 1, and so the other one should be 2. Yes, I had that in my notes. We should check that occasionally. All right, thank you very much. All right. Good thing I asked about C1, right? Okay. All right. Any questions there? Okay, so we're doing a lot of working with these solutions. Of course, we're skipping the most important part, right? And all these problems, I'm saying, here's a solution, U1. Here's a solution, U2. And we're learning a lot about the properties of solutions and how they work together to form the general solution. But the real question is how to actually find these solutions given the general system. And so that's what we're going to look at next. And once again, the big idea is it's just what we've done before. So once again, I'm going to kind of talk through what we did for our higher order systems, and we're going to use that as the roadmap. I don't want you to memorize a bunch of techniques. I want you to think about this broad process. To solve differential equations, we either transform the problem or the system or whatever into a form we can straight integrate. Or we take a guess at a solution with some parameters and try to find a process to figure out the parameters. When we did higher order differential equations like the one shown, we made a guess at our solution form. We guessed it was going to look like x equals e to the RT. That was our guess. And so all we had to do is figure out the values of r that actually made that true. So we needed to somehow generate an equation to find the right r values. So what did we do? We took the derivative. We took the second derivative. We plugged it in. And we were able to generate that auxiliary equation, which turned out to be some sort of polynomial. And that allowed us to figure out the right R values to form our solution. Same thing with systems. Okay? I'm going to assume that my solution looks like this. My solution looks like some vector x constants e to the lambda t. I mean, our guess even looks like our old guess, right? It's like an exponential, e to the lambda t, e to the rt. But I have a system here, though, so I'm going to throw a vector in front of it, right? But our guess pretty much looks the same. So if I knew what the right x was and the right lambda was, I could put them in here, and that would be my solutions. Okay? Now, how are we going to generate an equation to figure out what x is and what lambda is? Same way we always do. We're going to take a derivative and we're going to plug it into the equation. If this is u, then u prime is going to be, well, this is a vector of constants, so it's just going to sit there. And so I'm basically taking the derivative of e to the lambda t. That derivative should be lambda e to the lambda t. The derivative of e to the 2t is 2e to the 2t, right? Lambda some constant here. Now I'm going to plug it in. Looks like I have, if I plug it into my differential equation here, I'm going to have u prime, which looks like this, equal to my matrix A times u, which is x e to the lambda t. Now on both sides, I see e to the lambda t. Is e to the lambda t ever 0? It's not ever 0. It's the exponential. So I can actually divide by it because of that. So I divide through by that. It goes away. I'm going to rewrite it just like this. And this is actually a pretty special thing here. A times x is lambda x, because normally I have a vector looks like this. If I multiply this thing by some sort of matrix, it changes it. It changes the length of it, it changes the direction, it swaps through all over the place. I get some different vector. Right? It could be anything here. But this is a special situation. I have this vector, I multiply by this matrix, and all I do is scale it. I double it, I add it, and whatever I lengthen the vector, the direction isn't changing. It's kind of a special situation you really focus on in linear algebra. And the idea is that x here is going to be our eigenvector, and lambda is going to be our eigenvalue. And this is a known problem from linear algebra. And these are the eigenvectors and eigenvalues of the matrix A. So all I have to do is solve this eigenvalue equation, and then I'll figure out what lambda is, I'll figure out x is, put them into my assumption, and there's my solution. So that's pretty much what we do here. So here's an example. I have some differential equation. Rewrite it in the matrix vector form here. And now I'm telling you, here are the eigenvalues and eigenvectors. I took the matrix A, I calculated these guys. I figured out that lambda was equal to 1, and the associated eigenvector was negative 1, 1. All right, here's a value of lambda and a value of x. Well, great. If that's true, and my assumption was that my solution looked like x times e to the lambda t, then apparently one solution is going to be negative 1 to 1 e to the 1t. Like once I know those eigenvalues and eigenvectors, boom, there's my solution. Apparently my other solution is going to be the other eigenvector e to the other eigenvalue. And then if these two are linearly independent, which later on we'll show that they are, my general solution is just going to be C1 negative 1 1 e to the t plus C2 1 1 e to the 3t. And so the point here is there's really nothing to forming our solution after we calculate that eigenvalue. That's going to be the big step. Calculate eigenvalues and eigenvectors. Once we have values, roll them into our assumption. Okay? Any questions there? Yep. Right. So I have my system here. Okay. I assume here that my solution looks like some x e to the lambda t. And the last little algebra told me that x is the eigenvector and lambda is the eigenvalue of the matrix A. So I just need to calculate the eigenvalue and eigenvector. And if I do that, I'll know what lambda is and I'll know what x is. Okay, and so I'm just saying here they are, kind of avoiding the calculations. You can see what happens when we get them. So if I find these values, all I'm doing is plugging them in. I have an eigenvalue here, I plug it in for here. I have an eigenvector here, plug it in for here. And that forms one solution. Just like before, when I found my r's, found r's 1 and 3, well, either the 1t, either the 3t, right? Like that's how I found my solutions. Same thing here. Okay. So really, in general, that's what you do. You find the eigenvalues of A, you find the associated eigenvectors of A, you form your solution. That's the process. Okay. Yep. Yep. We'll get rid of some of these squigglies for you. What's that? I did. Wouldn't it be nice if I always did that? That's what we're going to do next. That's the fun part, right? That's the linear algebra part. I mean, I'm sure you all know it. You've all done it a bunch of times, and don't worry about the fact that it was right at the end of that linear algebra class, right? Where you were really focused for that last week of linear algebra, right? And probably didn't have much else to do that last week of the semester. So, and you probably had that class like, 2 years ago or something as well. So we'll go through that one pretty carefully. But that's the general idea. So you can see here, the big thing is to calculate the eigenvalues, eigenvectors. That's going to be the hard part. Okay. So how do we do that? Like I just write these steps here. It's not like this is some sort of magical recipe here. It just, I like to see lists, right? I'm a list person, so I like to write it down. It helps me organize my mind. But really the step is going to be to calculate the eigenpairs here. So I'm going to do the full-blown linear algebra reminder of how to calculate eigenvalues and eigenvectors. So if you're rusty, don't worry. I'm going to go through the whole process, right? You're strong on it. Relax a little bit here. Here's what we're going to do. There's really two equations we're going to work from. So first, I'm going to give you the general, not super theoretical, but the reason these equations are important, the reason why they're there. And I'm going to say we're going to do this and this, and that's how we're going to calculate them. The idea is we start with this equation. I take this equation, I subtract off. These are the steps that you're actually going to use. This is kind of where you get to the process. So if I were to subtract that over, I would get this thing. If I were to factor out the x, I would get an equation that looks like this. So some people will say that this is the eigenvalue, eigenvector equation. Some people say this is the eigenvector value. They're the same, one just leads to the other. This is the one that we're really going to use, though. Okay. And I want to use that to figure out lambda and x. The only problem is I have one equation. I have two unknowns. It's a problem here, okay? And so what I need to do is figure out another equation to help me find one of these things. Now first, I add a little I there. What's I? I is the identity matrix. And where did it come from? Well, if I redistribute this x, I would have this thing minus lambda I times x. The whole idea about the identity matrix is that identity times x is, well, just x. Now, the reason I had to add it is because I'm taking this matrix, which in general is like an n by n thing. I can't subtract 2 from this matrix. So the identity here gives me the right dimensions to do the subtraction. But it doesn't actually change the statement of the equation at all. It's still equivalent. Okay, so I have this guy. This is really just some matrix here, right? And so that system is the same thing as this system. Now, if I'm thinking about this system, b times x equals 0, I'm trying to solve it, figure out the x now. I could have 0 solutions to this thing, or I could have instead of many solutions, or one solution. Can I have 3 solutions? No, it's 0, 1 until none. Well, I'm looking at this thing, I can see one solution. Right? If x equals 0, that's got to work here. So I know I have 1. That's a really boring solution. I'm looking for eigenvectors. Eigenvectors are defined to be non-zero vectors x. Okay? So I want to find non-zero solutions. That tells me right away there must be infinitely many solutions here. Okay? Now, if there existed this guy, B inverse, if that guy existed, then this equation would be really easy to solve. I would just multiply both sides by B inverse. And over here I get x, and over here I get 0. And if B inverse existed, that would be the only solution to this equation. So the whole idea is B inverse better not exist. Okay? For me to have these eigenvectors, B inverse can't exist. Okay? And then what do I know about when B inverse exists or not exists? If the determinant of B is equal to 0, what does that tell me about the inverse? Doesn't exist, right? Think of that equation for the 2 by 2, like 1 over the determinant of A times some stuff. Well, the determinant of A is 0, 1 over 0 goes up, right? That's a whole big bad thing. So the idea is if the determinant is equal to 0, the inverse can't exist. And what do I want? I want this determinant not, or this matrix not to have an inverse. So for that to happen, for these eigenvectors to exist here, the determinant of this matrix has to be equal to 0. Okay? So that's the logic behind my other equation. And now basically I'm going to use these two equations to actually calculate the eigenvalues and eigenvectors. So the first equation is just the eigenvalue equation. And then I'm going to generate a second equation to actually solve for variables. I get this back to the idea that this inverse can exist. Okay? Now I have the two equations. I like the second equation, right? There's only one variable, lambda. So I'm going to use that one to figure out what the lambda is. And then I'll plug the lambdas into the first equation to figure out what the eigenvectors are. Okay? So that's the process. That's the idea. Let's go through a specific calculation here. Okay? What am I going to do? I'm going to solve that determinant equal to 0 to find my lambdas. So the very first time I'm going to do this, I'm going to show all the steps. And then I'm not going to do that anymore. Right? So first I want to calculate A minus lambda I, like that, the determinant. Your book will write this as det A minus lambda I, just different notation for the determinant. They're equivalent here. Well, what is this? Here's A minus lambda I. I is the identity matrix, the 2 by 2 identity matrix. But what happens when I multiply that identity matrix by lambda? I just get lambda on the diagonals, right? And then if I take this one and I subtract a matrix that just has lambdas on the diagonals, the net effect is just subtracting lambda on the diagonals. Okay? So I'm not going to write that in between step anymore. When I see A minus lambda I am just going to subtract lambdas on the diagonal. Okay? I just want to show you once to make sure you see why A minus lambda I is what it is. Okay? Now I'm going to calculate that determinant. I'm going to take that product, so I get 2 minus lambda squared minus the other product, so minus 1. That means I got 4 minus 4 lambda plus lambda squared minus 1. That means I got lambda squared minus 4 lambda plus 3. That guy factors into lambda minus 3, lambda minus 1. And the whole idea is trying to find the lambda values that make that thing equal to 0. So what are the eigenvalues here? The eigenvalues are 1 and 3. And the thing we're going to highlight later here is that this here is a 2 by 2 system. A 2 by 2 system. And in that process, I generated a second degree polynomial. And that correlation is going to continue, right? If I have an n by n system, I'm going to generate an nth degree polynomial. and it will have n roots. Okay, so we got that guy. So now I have our eigenvalues. Those are just the right values so that this thing has infinitely many solutions. So now I'm going to take lambda equals 1, the first one, and I'm going to plug it into that equation and solve for x. So I'm plugging that into a minus 1 times identity times x equals 0. And I'm solving for the vector x. Okay, once again, a minus 1 times I. That tells me I'm basically subtracting 1s off of the diagonal. So here's my matrix A up here. There's A. I subtract 1s off the diagonal. My system basically looks like 1, 1, 1, 1 times that vector x is equal to 0, 0. I'm solving for the x's here. I could write the augmented matrix if I want, and then do row operations. What are those row operations going to do for that augmented piece? So I do row operations. Are the zeros going to change at all? No. So I'm really lazy, so I never write them. So usually for a homogeneous system, we just augment this piece. I mean, we just row reduce this piece. Okay. So now I row reduce this piece, and I get 1, 1, 0, 0. Ooh, is that right? Does that make sense that I have this row of all zeros? I pretty much have to have the row of all zeros. If I don't, I wouldn't have any free variables, and I wouldn't have infinitely many solutions. So I expect to get a row of all zeros here. All right. Now I can translate this back into the equation it would generate. This says x1 plus x2 equals 0. Gives me the relationship between x1 and x2. If I want, I could solve that explicitly for one of them. And so then I'm trying to form my vector here, which is just the values of x1 and x2. And I can essentially choose x2 to be free. So it's a free, it can be anything it wants to be. I'll give it a parameter name. It's s. It can be anything it wants to be. But if it's s, what is x1? Negative s. They both have a factor of s in there. I factor it out. I get negative 1, 1. That happens every single time. Right? The eigenvectors are always going to be infinitely negative. It's always going to be some parameter times some vector. It happens all the time. Like I just stopped at x. That's what the vector. I would say the eigenvector is negative 1, 1. When I say the eigenvector is negative 1, 1, we all know that it's negative 1, 1, and any multiple. I won't even use that parameter s in there anymore. I'm just going to eigenvector is negative 1, 1. Okay? And so that's what I have here. Now I have the eigenpair. That is lambda equals 1. And my first eigenvector is negative 1, 1. I do the same thing with the other eigenvalue. Now let lambda equal 3 and do the same thing. Why don't you guys go ahead and calculate that second eigenvector. Subtracting 3 off the diagonal. Just kind of work through it, ask questions. Now we have minutes until we get to the homework. Go through the steps, and then once you get through it, you start to get more comfortable with it, and you can shortcut this. Just going to take a, subtract 3 off the diagonal, and then roll it instead. For a 2 by 2, I'm not even roll it instead, because I know the second one's going to go to 0. The larger system, I probably have to roll it up. All right, I take my matrix A up here, 2, 1, 1, 2. I subtract 3 off the diagonals. I get negative 1, 1, 1, negative 1. I row reduce that thing to get 1, -1, 0, 0. That tells me my equation is x1 minus x2 equals 0, or x1 equals x2. What's my second eigenvector? I'm not even going to use that parameter. I'm going to kind of generate a second way. Right? The idea is x2 is free. It can be whatever it wants. I'm just going to choose a value. I'm going to say if x2 is 1, what would x1 have to be? 1. There you go. I've just found one eigenvector, and I know that any multiple of it is also an eigenvector. So that's my second eigenvector. So now I know that my general solution is some constant, my first eigenvector, e to the 1 times t, C2, my second eigenvector, e to the 3t. If this, here we described a matrix, but if this matrix is the one from that system of differential equations. All right, questions? Yep. It's a good question. Let me go to my next. Any other questions first about the solution process here? Yep. You can think about it like that, right? From the linear algebra standpoint, no, because it's just that I'm building an eigenspace, and so any multiple of the eigenvector is also going to be an eigenvector. From forming the solution differential equation, you can certainly think about that, because in the end, we're taking any multiple of our eigenvector anyway. All right. So I know the problem here, but we're going to skip that and go on to our important linear algebra properties. All right. So there's a little list of these in the text as well. I kind of picked out, kind of rephrase them a little bit. And the idea is that we don't want to focus a ton of time on linear algebra theorems and theorems. But the idea is to be able to justify how we're forming our solution and to say things are linearly independent. We need a couple of core things from linear algebra eigenvalues. The first one says that if A is an n by n matrix, in this level of n by n matrices, then that determinant for each calculated, which is called the characteristic polynomial, that's going to be an nth degree polynomial. We're kind of talking about that already. We use an nth degree polynomial. The next piece says that, okay, how many roots are there going to be for that nth degree polynomial? Well, one, you decide, is it okay to have complex roots? We're going to say yes, it is okay to have complex roots. And then it says, counting according to multiplicity, the polynomial has n roots. Counting according to multiplicity. What does that mean? It just means that if your roots are like lambda equals 3, 3, 3, and 3, you're counting those as 4 roots. Okay? That's what counting according to multiplicity. If you have a repeated root, you're counting it that many times. That's what that means. So as long as we count the complex and we count the number of repeated roots, then we will always have n eigenvalues. Okay. Then a quick little thing just to state, if we have a complex eigenvalue, r plus I theta, whatever, then its complex conjugate is also an eigenvalue. So we don't have to calculate the second one, comes in the wash there. The next one says that for every eigenvalue, there will be at least one eigenvector. For every distinct eigenvalue, there will be at least one eigenvector. And the last one says that eigenvectors from distinct eigenvalues, that's supposed to be not LT, but LI, linearly independent. So the idea is this. Okay, we have our polynomial, we get n distinct values, right? We know from number 4 here that each one of those distinct eigenvalues is going to generate at least one eigenvector, so we're going to have an eigenvector. Since they're all coming from the same eigenvalues, that last one says they're going to be all linearly independent. That means we know they are forming a basis for the solution space. We don't have to check any Wronskians now. It's giving us that linearly independent. Right? Well, that's a lot of work for us to say, yeah, we're always linearly independent. Because they're really not. Right? So if they come from distinct eigenvalues, they are. If they're complex, that's still okay because we have a plus and a minus, but they're still considered different. They're still distinct here. But what if they're repeated? If I have lambda equals 3, 3, 3, and 3, if I have 4 3s, right, I'm guaranteed to get at least one eigenvector from there, but am I guaranteed to get 4 linearly independent eigenvectors from there? I am not. And that's the problem. Okay? So the hardest case will be again that repeated case, trying to figure out what to do if we don't get enough eigenvectors from that repeated eigenvalue. And so that will be the biggest issue there. All right, that is pretty much it. Tuesday, we will for sure return exams, take some questions and have that quiz. That quiz will include a basic eigenvalue, eigenvector calculation. All right, so it'll be that property stuff and at least one eigenvalue, eigenvector calculation.